Okay, in this example, we're going to be talking about a wire, and which basically means we're talking about a one-dimensional structure. Okay, the wire is stretched. You can kind of think about it going like this, just this tiny little thing. And it's going to be stretched where its left end is at x equals 0 and its right end is at x equals 4, and we're operating in feet. This is the English system. Okay, given the wire density, so the density of the wire varies as a function of x along this line here. And it's like this. Our wire density says e to the minus x. It's going to tell us, like, when I go farther out here, right, I've got a different density than I do here. So we want to be able to calculate the mass of our wire. Okay, we're going to break it up into two segments, first from 0 to 2 and then from 2 to 4. Okay, we're going to be able to show that the mass is going to be different between 0 and 2 and also from 2 to 4, okay, because the density of our wire is changing. Okay, we're going to use what they call a length density, which we call delta sub L, as a function of x in this case here. Okay, so to calculate the mass, I'm going to integrate from 0 to 2. I have my density, e to the minus x, okay, and I have my dx. So what's happening here is, along my wire, I'm going to break this wire up into tiny little slivers. These are my tiny little slivers of dx as I go. Tiny little sliver, tiny little sliver. I'm going to sum up all of those tiny little slivers from 0 to 2. Each of those slivers has a different density, right, because the density is varying along the pathway. Okay, so when I go to integrate this, I'm going to get minus e to the minus x, and I'm going to evaluate it from 0 to 2, which gives me e to the minus 2 minus a minus e to the 0, okay, which I'm going to write as 1 minus e to the minus 2. I can leave it like this, but I'm also going to approximate it as 0.864, and this is in, bear with me here, slugs, which is our English system for mass. Okay, this is our mass. Okay, this is our mass from 0 to 2. Now let's calculate the mass of our wire. We're going to go from 2 to 4 now. We're going to do the same thing. So I'm going to calculate my mass. I'm going to go from length 2 to length 4, my wire density, times those tiny little slivers. I'm going to add up all those tiny little slivers. So minus e to the minus x, and I'm going to evaluate it from 2 to 4, which gives me minus e to the minus 4 minus a minus e to the minus 2. Okay, when I add that up, I can leave it like this, right? Or I'm going to approximate it as a decimal 117, and this is in slugs. Okay, so that's our mass from 0 to 2, and that's our mass from 2 to 4. So you can see that by breaking up the wire into the first half and the second half, the left and the right, they're not equal in terms of mass. And the reason that they're not equal is because the density of wire changes as a function of x. Okay, right? Our mass gets different, right? Gets smaller as we go along this wire here. Okay, so now, leave that there. So now let's ask ourselves, where is the midpoint along this wire where the two masses are going to be equal to each other? I can't just split it right down the middle because we've just shown that that doesn't work. So I want to calculate our midpoint of mass. And that basically means I want the left and the right to be equal to each other, but the left of my midpoint and the right of my midpoint. So it means I've got an integral. I'm going to go from 0 to the midpoint, and I'm going to integrate what we've been doing before, and then I'm going to go from my midpoint to the end of my wire. Remember, we said the wire started at 0 and it ended at 4. I don't know where that midpoint is going to be. That's part of what I'm calculating right now. Okay, so I've got these two integrals that I do, kind of like what we just did, e to the minus x from 0 to x sub m for midpoint, minus e to the minus x from x sub m to 4. Okay, so now we have a bunch of algebra that we have to work through. So this is going to look like minus e to the minus x sub m. I'm going to go minus a minus e to the 0, and that's going to equal to minus e to the minus 4 minus a minus e to the minus x sub m. Okay, so now what I want to do is get all of the x sub m's on one side and all of the numbers on the other. So I'm going to add e to the minus 4, e to the minus 4. Now remember, these are just numbers. E to the 0, e to the minus 4, those are numbers. And I'm going to add e to the minus x sub m. I'm going to add e to the minus x sub m. So when I do this, I'm going to get, I'm going to call this 1 now. E to the 0 is 1 plus e to the minus 4 equals 2 e to the minus x of m, right? They're the same. I'm just going to sum them up. So now I'm going to divide both sides by 2. Let's continue it over here. So I'm going to get 1 plus e to the minus 4 divided by 2. This is a number. I could actually just calculate it through and get a decimal, but I'm going to leave it like that for now. Okay, now I want to get this x sub m out of my exponent, so that means I have to take the natural log of both sides. And when I take the natural log of this, I can bring down my exponent. Right, the natural log of e is just 1. So now I get natural log of 1 plus e to the minus 4 over 2 equals minus x of m. The minus came from before. So I'm going to divide through by minus 1. So I'm going to get minus natural log of 1 plus e to the minus 4 over 2 equals my x of m. So now I'm actually going to plug in those numbers, take the natural log, multiply it by a negative 1. My x of m, when I do that out, is 0.674 feet. Okay, so where, that's like right about here, roughly speaking. Okay, maybe I over-exaggerated. But what that means is that the mass on this side of the wire is equal to the mass on that side of the wire. And that's because the density of our wire is changing as we go along that wire.